Hello everyone, thanks for joining this presentation on PipeComm. My name is Xu Ruifan and I'm a PhD student at Peking University. My advisor is Liang Yun, and today I'm excited to present our work, PipeComm Maximizing Link Utilization through Pipeline-Aware Collective Communication Synthesis. AI is everywhere. We see deep learning driving graph processing, scientific computing, recommendation systems, autonomous driving, and of course, large language model chatbots. Almost every domain relies on increasingly powerful neural networks, but with that power comes a cost. As this plot shows, model sizes have grown from about 100 million parameters in 2018 to well over a trillion today, and the trend continues upward. A single GPU or even a single node can no longer hold or train these models. This forces us to adopt distributed training across multiple nodes. Both continue to scale, and we push to even larger clusters. Communication overhead becomes a first-class bottleneck, not an afterthought. This table shows the breakdown of training time for several popular large language models, including Llama 2 and GPT-3 across different parameter sizes. You can see that a significant portion of time is spent on computation, but importantly, communication already takes up a noticeable share, and this is just in these specific configurations. To address this communication bottleneck, hardware vendors have introduced supernodes systems that tightly couple a large number of accelerators within a single high-bandwidth domain. For example, NVIDIA's NVL72 connects 72 GPUs through NVLink into one unified domain. Before diving into our approach, let's first establish some background on the communication primitives that distributed training relies on. All the parallelism strategies we just mentioned are ultimately built on top of a small set of collective communication operations, so understanding these is essential. The first is the reduce scatter, which reduces the data across nodes, for example, by summation, and then scatters to the partial results, so each node ends up holding one slice of the final output. Gather, which does the opposite. Every node gathers all the trunks from all other nodes. Combining these two gives us a reduce followed by a broadcast, so that every node obtains the complete reduced result. This is the most common operation for gradient synchronization in data parallelism. O2O has each node exchange distinct data with every other node, which is essential for mixture of experts and expert parallelism. These four primitives are exactly what we aim to synthesize efficiently, and as we'll see next, doing so on heterogeneous topologies is far from trivial. Today's distributed systems are highly heterogeneous in both bandwidth and latency. As shown on the left, communications span multiple hierarchy levels, on-chip, intranode, and internode, each with different latency and bandwidth. And as shown on the right, modern multi-chip accelerators often have asymmetric links, so connectivity and bandwidth vary across nodes. This heterogeneity makes traditional topology-agnostic methods inefficient, motivating topology-aware communication synthesis that fully exploits the network. Look at the topology in this figure. It's a 2D mesh, but crucially, the horizontal links have a different bandwidth with the vertical ones. And we'll use altogether as our examples here. Let's see how an existing tree-based method handles this. In the middle, altogether propagates the data downward over 3 steps until every node holds all the 4 trunks. The bandwidth table on the right shows which links are active at each step. The problem is the fast red links and the slow blue links links are not used uniformly. In some steps, the faster links sit idle. Since the schedule is fixed and topology agnostic, it cannot keep all the links busy. More advanced graph-based synthesizers improves the tree approach by allowing more flexible transfer patterns across the topology. In the middle, you can see that it uses both red and blue links more aggressively at each step, but even this approach still completes altogether in 3 steps, because the schedule is generated greatly within a single iteration. It still cannot balance the fast and slow links. As a result, both approach bandwidth utilization remains merely 67%, the same limitation as before. The idea is to introduce pipeline scheduling. By using links across multiple iterations, we can significantly improve overall bandwidth utilization. Unlike traditional methods, our approach explicitly considers potential resource conflicts during the scheduling phases, thus to coordinate communication resources more effectively and alleviate the bottlenecks. Here, we construct a pipeline communication scheme where the transmission cost for a single data trunk may increase slightly, but the step 1, 2, 3, and 4 can now execute in parallel within the other steps. Ultimately, the entire communication algorithm forms a 2-stage pipeline structure. This achieves full coverage and utilization of all links, dramatically improving the overall efficiency. An overview of PipeComm. The framework takes 2 inputs, user-provided programmable primitives, and the workload and topology description. The primitives are divided into 2 categories. Communication primitives define the basic operations like broadcast and reduce, and the construction primitives provide guidance for the pattern building, such as interleaving and reversal. With these inputs, we first perform communication pattern construction. In this step, we use MILP encoding to ensure correctness, assign proper depths, and prevent congestion. Next, the pipeline schedule generation step assigns concrete time slots to each data transfer, respecting resource conflicts across the overlapping iterations. The final output is a communication algorithm that is both correct and highly effective, ready to be deployed. In the following slides, I will show you how each component works in detail. It can naturally be decomposed into 2 phases. A reduce phase. During the reduce phase, all nodes aggregate their data into the full summation at the node 0. Then, in the broadcast phase, that result is distributed back to every node. The key observation is on the right. The reduced and broadcast trees are structurally complementary. The broadcast tree is essentially the reduced tree reversed. This complementary is what lets us overlap the 2 phases in a pipeline, which is the core idea behind our 2-phase pipeline algorithm. In the first phase, the system generates a concrete communication scheme tailored to the target topology. As shown in the figure on the right, to avoid bandwidth conflicts between different communication rounds, the original topology is decomposed into multiple communication patterns. We propose a MILP-based approach to construct an optimal communication pattern. We define 2 sets of decision variables. X is a binary variable indicating whether the edge E is used by the pattern S, and L is a non-negative real variable representing the depth of node V in pattern S. The flow conservation constraint ensures that every node except the root receives the data exactly once. This guarantees a train-shaped broadcast pattern rooted at each source. The link capacity constraint is the key for pipelining. It limits the number of patterns that can use a given edge E within one initial interval. The right-hand side, II divided W, ensures that the total number of trunk transmissions mapped to a link does not exceed its temporal capacity. And the depth constraints relate the depth of a node to its predecessor. If one edge UV is selected, then the LSV must equals LSU plus the link delay W. A large constant M deactivates these constraints when the edge is not used. The solver minimizes the overall depth subject to all constraints, producing an optimal congestion-free communication pattern. This MLP formulation gives us probably optimal patterns for small to medium topologies. Solver-based version, we also propose an incremental strategy that scales to much larger topologies. As shown in the flowchart on the left, starting with the initial topology, we iteratively construct communication patterns and compute the residual graph, and the link are not used yet. We keep adding patterns until the initial interval would increase at the point we have the optimal candidate. The increased II track. As we add the patterns, we track the residual graph. When the remaining links can no longer absorb new pattern without raising the II, we instead allow the II to increase, shown here as the transition from sparse residual graph to a denser increased graph. The initialization interval is increased. We go back to pattern construction and iteratively find new patterns to fill the additional capacity. As shown right, starting from the increased graph, we extract a sequence of new patterns, and the link that remains unused forms the new residual graph highlighted in blue. Basic pipeline, we can push utilization even further with broadcast reduced overlapping. The key observation is shown in the top right. When we run broadcast pattern alone, several links stay idle, and the bandwidth is not fully used. Since reduce and broadcast are structurally complementary, their idle links don't overlap. So instead of running them separately, we overlap them in the pipeline, as shown in the bottom. The two patterns fill each other's gap. This further optimization pushes bandwidth utilization from 67% all the way up to 100%. This pipeline scheduling, which assigns each transfers into a concrete time step. As shown on the left, successive iterations are launched one initiation interval apart, so they may be overlap. But this overlap can cause link congestion if two iterations try to use the same link at the same time. And here is a concrete pipeline example. Each square represents a transfer, different iterations in different color. Do we guarantee that overlapping iterations never congest in the same link? The key insight is that the pipeline is periodical. A new iteration starts every II steps, so the link usage simply repeats with period II. This lets us trace the link usage compactly with a reservation table indexed by the link and step mode II. From this, we get a simple congestion-free conditions. Two transfers conflict only if they fall in the same slot. Keeping their slots distinct guarantees no congestion, as shown on the left, where 5 iteration pipeline cleanly without congestion. The alpha-beta model, we analyze the pipeline cost. With data D split into C trunks, the total step count is S plus II times C minus 1, giving a total cost that decomposes into a latency term alpha and a bandwidth term beta. We can find the optimal trunk count, and this equation is dependent on the trunk size. The optimal trunk count C star can follows a simple square root formula, so the optimal partition can be determined in the analytically, yielding a tight lower bound and guiding our trunk selection in practice. To make our approach flexible, we expose a set of programmable primitives. The first category is the communication primitive, which defines the basic functionality for collective communication through reduce-at broadcast plus two compiler-inspired techniques, tile and pipeline, for better link utilization. Here's an example that uses these primitives together to express a topology-aware pipeline algorithm. Category is the construction primitive, which lets users guide how communication patterns are built. With interleave and reverse, partial patterns can be efficiently composed into full or reduced patterns. We also introduce hierarchical construction via extend, which expands the pattern based on a given subtopology. As shown here, a small schedule on a subtopology is scaled up across the full network. We introduce our evaluation setup. We compare against two classes of baseline, heuristic approaches and solver-based approaches. Our method comes into two versions, a solver-based variant and an incremental variant. As shown in the table, we evaluate across a range of topologies under both homogeneous and heterogeneous bandwidth settings. It compares our two strategies against heuristic baseline on our reduce. Across all four topologies, both versions consistently outperform existing methods, with the advantage most pronounced on the heterogeneous networks, where our pipelining effectively balances fast and slow links. Overall, we achieve a 1.39 times average speedup over the heuristic approaches. Pipeline scheduling, our link bandwidth utilization consistently stays above 80% throughout the entire communication phase. In contrast, other approaches often suffer from long idle periods at the beginning and a rapid drop in utilization toward the end. The table on the right reports synthesis time and bandwidth. Our methods not only deliver more than 1.5 times speed up on large size transfers, but also generate schedules in a fraction of time. It's not limited to all reduce. It naturally extends to other collective operations, including all-gather and all-to-all. For all-gather, every node initiates a broadcast. Although all-gather lacks the broadcast reduce overlapping that benefits all-reduce, our pipeline scheduling still achieves a 1.26 times speedup over existing methods. For all-to-all, which requires a dedicated communication path between every pair of nodes, existing works suffer from extremely inefficient modeling. In contrast, our optimal solver-based strategy nearly saturating the theoretical limit. These results confirm that PipeComm is both general and efficient. We present three additional experiments. End-to-end on real-world workloads, we reduced exposed communication and achieved 1.43 times and 1.12 times speedups over the baselines. As for GPU evaluations on a real 16 GPU system, our solver-based approach outperforms Nickel and Tacos with a 1.12 times speed up. And as for scalability, the incremental approach scales to thousands of times with only the square of node times synthesis time, far cheaper than the solver-based variant. Together, this confirms that our approach is both efficient and practical at scale. We summarize what we have presented. First, PipeComm introduced a two-phase synthesis algorithm, pattern construction followed by pipeline schedule generation. Second, we develop an efficient overlapping method that concurrently schedules, broadcast, and reduce operations within the same pipeline. Finally, PipeComm is fully open sourced, and you can find the code at the link shown here. That's all for my presentation. Thanks for your listening.